Hello everyone. My name is Valeria Tafintseva. I am a researcher in data science at Norwegian University of Life Sciences. Today we are going to talk about basic regression and machine learning. First, shortly about history. The term machine learning was introduced in 1959 by Arthur Lee Samuel, an American IBMer and pioneer in the field of computer gaming and artificial intelligence. Also, the synonym self-teaching computers was used in this time period. Machine learning appeared within the field of artificial intelligence. In the early days of machine learning as an academic discipline, some researchers were interested in having machines learn from data. Machine learning as a separate field started to expand in the 1990s. The focus of the field moved from achieving artificial intelligence to tackling solvable real-life problems. It shifted focus away from the symbolic approaches it had inherited from artificial intelligence and towards methods and models borrowed from statistics and probability theory. Modern-day machine learning has two objectives. One is to classify data based on models which have been developed. The other purpose is to make predictions for future outcomes based on these models. Examples can be an algorithm specific to classifying data may use X-ray images coupled with supervised learning in order to train it to classify as cancerous or not. A machine learning algorithm for stock trading may inform the trader of future potential predictions, or self-driving cars, for example, learn to avoid obstacles and detect pedestrians. So, machine learning is the study of computer algorithms that can improve automatically through experience and by the use of data. It's seen as a part of artificial intelligence. Machine learning algorithms build a model based on sample data known as training data in order to make predictions or decisions without being explicitly programmed to do so. But what is data? Let us first discuss what it is strictly speaking. Data is a set of values of quantitative or qualitative variables about one or more persons or objects. Examples of data can be students' grades on exam, population survey, healthcare data, and many other. Often used term in machine learning that is related to data is a term feature. Features are values of qualitative or quantitative variables that describe each object. We can consider as feature, for example, age of person, gender, ethnicity, their income, and other type of explaining features. Let us consider an example. The famous iris flower dataset or Fisher's iris dataset is a multivariate dataset introduced by the British statistician and biologist Ronald Fisher in his 1936 paper, The Use of Multiple Measurements in Taxonomic Problems. It is sometimes called Anderson's iris dataset because Edgard Anderson collected the data to quantify the morphologic variation of iris flowers of three related species: Iris setosa, Iris versicolor, and Iris virginica. To do that, 50 flowers of each species were measured, resulting in the data set of 150 samples, or objects in the data. For each sample, 4 different measurements were taken: sepal length, sepal width, petal length, and petal width. You can see it on the figure. So these are so-called features or attributes. Each sample has so-called label or response variable. This is the class belongingness of each sample. So let us summarize. A data matrix is a set of measurements for individual objects which are usually put in rows, while the measurements or features are put in columns. In machine learning and pattern recognition, a feature is an individual measurable property or characteristic of a phenomenon. Choosing informative, discriminating, and independent features is a crucial element of effective algorithms in pattern recognition, in classification, and regression. A numerical feature can be conveniently described by a feature vector, and the vector space associated with these vectors is often called the feature space. In order to reduce the dimensionality of the feature space, a number of dimensionality reduction techniques can be employed. In terms of machine learning, a convention is to denote the feature matrix by matrix X, while a matrix of responses by Y. So let's put this data into a machine learning framework. Assume X are observed variables, Y are hidden variables. A training set is a finite set of pairs X and Y, which consists of observed variables inputs and known values of the corresponding hidden variables outputs. The goal of machine learning is to find an algorithm that can learn a decision rule using training set and make predictions of unknown hidden variables on a new set, which is not seen by an algorithm of the observed variables. Machine learning approaches can be divided into 4 categories to do these tasks, depending on the nature of the signal or feedback available to the learning system. There are so-called supervised learning tasks. This is when the computer is presented with example inputs and their desired outputs given by a teacher. And the goal is to learn a general rule that maps inputs to outputs. Unsupervised learning is when we don't have labels given us by or to algorithm, leaving it on its own to find structure in its inputs. Unsupervised learning can be a goal in itself, discovering hidden patterns in the data or finding new features in the data. So-called semi-supervised learning is a combination of supervised and unsupervised learning. A subset of data is labeled or given their outputs, and the rest is not. Then we make a model on the labeled data and the pseudo-label, the unlabeled data. Then we use the full data set, labeled and pseudo-labeled, to build a final model. Reinforcement learning, a computer program, it's when the computer program interacts with a dynamic environment in which it must perform a certain goal, such as driving a vehicle or playing a game against an opponent. As it navigates its problem space, the program is provided feedback that's analogous to reward, which is tries to optimize. So supervised learning algorithm builds a mathematical model or of a set of data that contains both the inputs and the desired outputs. Depending on the nature of the response or output, there are following tasks that can be solved by machine learning. When y is a discrete variable, the supervised learning problem is a classification problem. A discrete variable is, for example, a variable describing classes, disease, for example, or levels of some disease. In such a case, we are dealing with a limited number of groups. When we have just 2 classes, we have so-called binary classification problem. So we need to discriminate 2 classes, for example. When we are dealing with more than 2 classes, non-overlapping classes, that's when we are dealing with multi-class classification problem. As an example of 3 classes here. When y is continuous, the supervised learning problem is a regression problem. A continuous variable is a variable whose values are obtained by measuring. That is one which can take an uncountable set of values. Such data can be a concentration of some chemical, for example, fat in milk or sugar in blood. Continuous variable can be turned into discrete if we aggregate the variable values to a limited amount of bins. That we get, for example, when we aggregate values for the blood sugar, and blood sugar can be low, medium, or high, described by just 3 groups. So thus the regression problem can be turned into a classification problem, which may be easier to solve. Let us talk about model. What is a model? First, we need to differentiate between terms like algorithm and model. An algorithm is a machine learning. In machine learning is a procedure that is run on data to create a machine learning model. Machine learning algorithms perform pattern recognition. Algorithms learn from data or are fit on a dataset. The goal is to choose a parameterized function p of theta and using training dataset optimize the parameters theta. So when we approximate the model, that's when we fix parameters, we obtain a p small model, which is trained on our dataset. But the core objective of the learner is to generalize from its experience, and generalization in this context is the ability of a learning machine to perform accurately on new unseen data, which have not been used to train the model. So the training examples, the training samples come from some generally unknown probability distribution, and the learner has to build a general model about this space that enables it to produce sufficiently accurate predictions in new cases. To do that, to find this out, we need to evaluate our model on an unseen data. How we do this? For this, we need to split our data into a training set and a test set. We build the model on the training set, and we need to test this model using test set. So the model is used on the new samples, and the labels are predicted, and then we need to compare these labels with the actual labels we know of the test set. So let us consider what type of models we can build. 2 big classes of machine learning models are linear and nonlinear models. Linear models are linear functions of theta. In such a case, we get linear decision boundary. An example of it can be a linear regression model. Nonlinear models are nonlinear in parameter theta. So the decision boundaries are nonlinear in this case. Many algorithms can be examples. One of them is, for example, artificial neural networks. And many algorithms, for example, logistic regression or support vector machines, are linear, but can be turned into nonlinear algorithms by considering constructing nonlinear features and using nonlinear kernels, for example. Machine learning also has strong ties to optimization. Many problems are formulated as minimization of some loss function on a training set of examples. Loss function is a learning metric to calculate the model errors. Loss functions express the discrepancy between the predictions of the model being trained and the actual problem instances. For example, in classification, one wants to assign a label to objects, and models are trained to correctly predict the pre-assigned labels. Loss function in such a case can be accuracy of such prediction when comparing assigned labels and actual labels. Typical examples from regression is root mean square error. Here the error is calculated using differences between the predictions of the model being trained and the actual problem instances. So we know the actual values y, and we get predicted values y hat, and we want to see the difference between them. The loss function is used to optimize the parameters and select the best model for the classification or regression. The difference between optimization and machine learning arises from the concept of generalization. While optimization algorithms are only focusing on optimizing the algorithm on the training set, machine learning is concerned with minimizing the loss on unseen samples. So characterizing the generalization of various learning algorithms is an active topic of current research, and especially in deep learning algorithms. So, when the model fails predicting unseen data, that is when overfitting occurs. And this happens when the model is too complex, or when it fits well only training dataset. Here I want to present an example where the training data is perfectly fit by a nonlinear model. So you see here points in black. These are the training points, and they are perfectly fit by nonlinear model in red. Whereas when we if we look for on the test points in gray, that is when you see they are not fit so well by the nonlinear model, and especially the points to the ends here, they will be not predicted well because the model is completely going wrong direction. But we see, for example, a simple linear model can fit very well both training set in black and test set in gray. So these are the comparisons of the models for the normal data we have. It's very easy to overfit on the training set and not being able to predict well the test set. So there are approaches to reduce overfitting, and these are the following. One of them is regularization. Regularization puts restrictions on model complexity, that is parameters theta. We can also minimize the number of parameters, and we can validate our models. This can be done by cross-validation and by independent testing. With this, I want to go into analysis of a real data set. And here I present IRIS dataset, which we talked about at the beginning, which I analyze in a software called Orange or Quasar. This is a software provided available freely by University in Ljubljana in Slovenia. And here I present a scatter plot. You can see along x-axis we have sepal width, and we have along y-axis sepal length, and each sample is presented by point. The colors here and the shapes are represented by 3 different species of iris: Iris setosa, Iris versicolor, and Iris virginica. When we apply classification, if we want to discriminate these 3 species, we can use numerous methods of machine learning. One of them is artificial neural network. Here you see how the method performs on this data to classify, and we see several misclassifications of the samples, like one sample here, 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 and others. So we have not a perfectly correct model. I forgot to say the colors here represent classifications, and the shapes of the points are actual labels of the samples. And when we look at the decision tree classifier here, we see other types of misclassification here a lot compared to the previous. So each method is different in its way and builds differently the decision boundaries. KNN here, K nearest neighbors, is presented in this figure. We also see that the boundary is different. Here is one sample, for example, misclassified. These samples here are also differently classified, and so on. So it's always nice to compare different methods. Regression, here we can, it's a different problem we can consider for this data set. For example, regression allows approximating the dependencies in the data. For example, here it shows how petal length depends on petal width. So the petal width along x-axis and petal length along y-axis, and the regression line here represents how well the data is correlated to each other. Unsupervised learning can be also applied to this data, and that's when we don't take our labels into account. So we only learn a pattern in the data by algorithm without knowing the labels. Here is an example of k-means algorithm, which finds patterns in the data set. And we can see, for example, that this algorithm finds that this sample is actually belonging and close to the cloud, to the main cloud of all samples here. But you can also see that the labels are not given. So the algorithm doesn't really know what is this sample. With this, I would like to give you a little bit of a literature for further reading, and I would like to thank you for your attention.